In the discussion of stratigraphy, we need to also discuss about the thickness of the geological layers. This is important because sometimes the pinching of the strata or the continuation of the strata are discussed. Several layers as continuity are discussed. Now, I start the discussion with consideration of parallel boundaries of any geological layer or geological body. These two lines Mn and Qp are considered parallel to each other. So, if we define a layer in this way, definition of a true thickness or orthogonal thickness or simply what is known as thickness represented by omega or sometimes by W is given by this thickness of the layer. So, this line along which the measurement is done is perpendicular to Mn line and obviously it is also perpendicular to the Qp line. Now, there are geological cases where the geological boundaries of a layer are non-parallel such as what I have drawn or they are curved, and in those cases definition of orthogonal thickness omega or true thickness or just call it a thickness becomes problematic, but there are ways to handle also. Any thickness measured not along this line will be called the apparent thickness represented by small a. So, for this geological layer shown by the blue lines, this line if a thickness is measured along this is called apparent thickness. There are two special types of apparent thicknesses commonly called. One is the horizontal thickness H, this line of measurement is horizontal, or V which is a vertical thickness. For example, if I measure the thickness of the layer along this, we call it a vertical thickness. The question is, why not we always measure the orthogonal thickness? Why are we bringing apparent thickness concept within geological case? Imagine we are doing a vertical drilling on a dipping geological body. So, this is a dipping geological body and a vertical drilling has been done. Then the thickness encountered for the layer along the drill direction is only known. So, this becomes my vertical thickness. Or consider an inclined or a directional drilling situation. For example, or why it is being performed, we want to understand. T is the target where there are some horizontal layers and just above the T there is two hard rock material. It is so hard that by normal drilling process it becomes very difficult to drill. Diamond drilling might be required, but then that drilling is very expensive. So, instead of going vertically down from S2 towards T, we may choose an area S1 and from here the drilling can start. And by an inclined drilling we can reach the target T. While drilling we may understand that there are some hard rocks encountered at several places. So, the drill direction can be changed with time and then we can reach over here. The change of drilling direction during the process of drilling is known as geosteering, an important engineering subject related to petroleum geoscience. So, if this inclined drilling is done and the target is over here, imagine the layers were horizontal and then by inclined drilling we have found the thickness which is A. So, we are not getting the orthogonal thickness. So, due to these constraints, the concept of apparent thickness has come into existence. As I said, above the target T, suppose there is a hard rock, there can be other possibilities which can force us to go for inclined drilling. Say this is a hill and for some reason I am interested to reach this target and here is a flat land. Instead of going at the top of the hill and drilling vertically down, it can prove easier to do a directional drilling from this point A reaching towards target T. Or instead of hill, suppose there is a building which I cannot break, a very important building is there, I cannot break, I cannot go vertically down, so I have to go for an inclined drilling. Or consider here this is a river is flowing or a disputed area or the boundary between two countries, or for some reason the geoscientist cannot reach this place, then also they will go for incline drilling. So, in all these cases the apparent thickness becomes important. Now, we are going to see the relation amongst omega, theta and A. A can be represented by V in one case, H in another case, and we can also take A in a case which is neither V nor H. That means an apparent thickness which is neither measured vertically nor measured horizontally. We will see them one by one. Let us take a case of a dipping geological body shown by these two red lines, and here omega is defined by the line AB. AB is equal to omega, the orthogonal thickness. So, this angle ABC has to be 90 degree, and the vertical thickness V can be defined. Now, we can define triangle ABC, which is a right angle triangle. This angle is 90 degree. Now, note, if the dip of the geological layer is theta, in that case this angle is 90 degree minus theta. Why so? Because when V was defined, this angle was 90 degree. Out of this 90 degree, a part of it is theta, so rest will be 90 degree minus theta. Now, let us move inside ABC triangle and we find that angle ACB is equal to 90 minus theta. This angle is 90 degrees, so therefore, this angle has to be theta. That is what is shown directly in the figure. So, in the triangle ABC, if this angle is theta, I can write cos theta is equal to base, which is here omega. This side is attached with the theta angle, so base is here, and then V, which is the highest length of the side. From here I can say omega is equal to V cos theta. Now, this looks correct, because if I take theta is equal to 0 degree or a horizontal unit, what happens in this case? As this diagram shows, omega, the orthogonal thickness, is equal to the vertical thickness, and this also comes from equation 1. If I put here theta equal to 0 degree, cos 0 degree equal to 1, that leads to omega is equal to V, which means my common sense inference is matching with what has been deduced. So, this is correct. We will now take a second case where the horizontal thickness is taken H, is a special kind of apparent thickness. Theta is the dip of the geological layer. Omega is the orthogonal thickness AB line. AB is equal to omega, and I wrote BC length is equal to the horizontal thickness H, which is a kind of apparent thickness A. Now, within the triangle ABC, I observe that this angle is 90 degree, angle BAC is equal to 90 degree, and if this angle is theta, since these two lines are parallel to each other, this angle is also theta. If this angle is theta and that these lines are parallel and cut by a line over here, if this angle is theta, this angle also has to be theta. So, we have established triangle ABC, we have conceived triangle ABC where angle BAC is 90 degree and one of the angles is theta. I will now write sin theta is equal to omega, this divided by H. So, from here I can write omega is equal to H sin theta. Now, this also looks correct, because if I take theta equal to 90 degree, such as a vertical layer, what happens? Omega, orthogonal thickness, becomes equals to the horizontal thickness. I can put theta equal to 90 degree in this equation. Since sin 90 is equal to 1, omega becomes equal to H, and that is happening over here. So, in this way I am sure that what I have deduced, omega equal to H sin theta, is correct. Now, from equation 1 and 2, where is equation 1? It is over here, omega equal to V cos theta, and equation 2, omega equal to h sin theta, we can say v cos theta equal to h sin theta. From here I can write tan theta is equal to v divided by h. V divided by h is equal to sin theta divided by cos theta. Tan theta equal to v by h. Let us take it forward. Tan theta equal to v by h looks logical with the diagram, because if h is the horizontal thickness, v is the vertical thickness, theta is the dip of the plane. If this is theta, then this is angle is also theta. These two lines are parallel and horizontal. If this angle is theta and it is this line and that line are parallel, so therefore that angle also has to be theta. Now within the triangle ABC, what do we see? Angle CAB is equal to 90 degree. This angle is equal to 90 degree, and here we can write tan theta equal to v divided by h. So this looks logical. So whatever has been deduced so far are all logical deductions. So I can call this equation 3, but it is too obvious. Look at the thickness issue when the apparent thickness is measured neither vertically nor horizontally. That means we are going to deal with an apparent thickness A, which is neither V nor H. A geological body dips towards my right hand side, shown by the red lines, and it has a dip of theta angle. Here an apparent thickness has been measured along the AB line. You can see this AB line over here, and the apparent thickness measured, that means the AB length from here up to here is the A1 unit. This AB line makes a plunge of phi 1 angle. What is phi 1? This is the plunge of the AB line. Now we want to find out a relationship amongst the dip of the plane, the dip of the geological body, A1 apparent thickness, which is the AB length, omega the orthogonal thickness which I have drawn by AC line. AC line is the omega or the orthogonal thickness in the diagram, and phi 1 is the plunge of the AB line, plunge of the drilling direction along which the apparent thickness is measured. Phi 1 is the plunge of inclined drilling direction along which the apparent thickness A1 is measured. Here one important constraint is there we have considered. We will start with this simplistic case and we will see later the complicated situations. We are considering that the trend of the AB line is same as the dip direction of the geological layer. In this case, this geological layer is dipping towards the right hand side and the line AB is plunging towards the right hand side. Now this right hand side can be geographic north, it can be geographic south, whatever be it, east, west, northeast or southwest or south, southeast. Both the trend of AB line and the dip direction of the geological layer are same. This is a crucial consideration, after which we are proceeding with the solution. And I repeat, we will see more generalized cases later. Now, to find out a relationship amongst theta, A1, omega and phi 1, I have constructed a right angle triangle ABC in the diagram. So, if I draw now, this is the AC line and this is the BC line and here is the AB line. Since omega is the orthogonal thickness, so this angle has to be 90 degree. Now, this triangle I can draw separately over here, so that things become very clear. AC is the orthogonal thickness omega, and AB length is the A1 distance. We draw in this original diagram a black line which is horizontal. Since this line is horizontal and this line is also horizontal, so what I can say, if this angle is theta, then this entire angle has to be theta. Now, since this line is also horizontal and this line is also horizontal, and if this angle is phi 1, this angle also has to be phi 1. So, from here we get another angle, theta minus phi 1 is this angle. If that angle is theta minus phi 1, this angle has to be same as this angle, which is the theta minus phi 1. Now, I take this over here in the clean diagram, and now I have a right angle triangle. If I write sine of this angle theta minus phi 1, or I am writing basically sine of angle CBA, what it will be? Omega divided by A1, that is what is stated. So, from here take A1 in this side, we write omega is equal to A1 sine theta minus phi 1. This is the relationship amongst omega, theta, phi 1 and A1. The relationship has been established. Now, we need to see whether the relationship is correct. Take a simple case of phi 1 is equal to 0. That means, the AB line has a plunge of 0 degree, or it is a horizontal line. So, instead of A1 thickness, as per the previous notation, I will write H. So, here I will write omega is equal to A1 becomes H, and this becomes sine theta, because phi 1 is 0. So, I get a relation omega is equal to H sine theta. Now, if I go back to our equation 2, I get the same relation already established, omega is equal to H sine theta. So, which means that the deduction has been done is correct and it matches with the previous equation. So, it looks therefore, this deduction is correct, omega is equal to A1 sine theta minus phi 1. Here, if you see the diagram clearly, the phi 1 angle was less than the theta 1 angle. Here, if you see the diagram, we have considered phi 1 less than theta. Now, what if phi 1 is more than theta? Will this relation change, or what will happen? I will leave up to the students to check by drawing new diagram. So, I write the equation again, omega equal to A1 sine theta minus phi 1. What if phi 1 is equal to 90 degree? That means, the vertical thickness has been considered. That means, A1 will be replaced by the symbol V. So, here we can, from here we can say omega equal to A1 becomes V sine theta minus 90 degree. Now, does it match with our equation 1? That is the question I am asking to students to check. This was our equation 1, omega equal to V cos theta. If I ask you what is the physical meaning of phi 1 equal to 90 degree, well, it is already stated that the drilling was done in a vertical manner. In these kinds of expressions or these kinds of deduction, we can simplify further. If I put theta is equal to 90 degree, that means the geological unit is vertical. We can also put theta equal to 0 degree, meaning horizontal geological body, and you can check. I am going to take a second case. What if the trend of AB line along which the apparent dip was measured is trending opposite to the dip direction of the geological body? Again, this is a special case and we will see general case much later. So, what is the situation? Here the geological body is dipping to the right hand side, and apparent thickness has been measured along this incline drilling. We can see that this line is having downside in this direction. So, which means the trend of this AB line is 180 degree opposite to the dip direction of the geological body. What it means? If this geographic direction is north, that direction has to be south. If this direction is northeast, that direction has to be southwest. If it is given that this direction is 30 degree north, this direction has to be 30 degree plus 180 degree is equal to 210 degree north, etc. So, how to proceed? To find a relationship amongst theta, phi 2, omega and A2. What is A2 here? A2 is now the AB length. Note, when I used A1 in the previous case, the plunge of the drilling direction was considered as phi 1, and when I am considering A2, the plunge of the drilling direction is considered phi 2. This is a case when the drilling direction and the dip direction of the unit of the geological layer are same, and this is the case when the dip direction of the geological unit and the drilling direction are 180 degree opposite to each other. This is the significance of using the suffixes 1 and 2 in my example. Okay. So, how to find a relation amongst these 4 parameters? What to do? I have to draw a horizontal line passing through point B. So, this is a horizontal line, this is also a horizontal line. So, if this angle is theta degree, this angle also has to be theta degree, and this line is having a plunge of phi 2. Now, this line is horizontal, that line is also horizontal. So, if this is phi 2, this angle also has to be phi 2. So, in total, if I draw the triangle ABC outside for a clearer view, the angle ABC, this angle becomes theta plus phi 2. Note, in our previous case we got an expression theta minus phi 1, here I am getting theta plus phi 2. So, this AC thickness is the orthogonal thickness omega. Now, since it is orthogonal thickness, this angle has to be 90 degrees. So, this angle is 90. So, in the right angle triangle ABC, I can say sine of this angle is equal to omega divided by A2. This is AB length is A2. So, from here I can say omega equal to A2 sine theta plus phi 2. The previous expression omega equal to A1 sine theta minus phi 1 and the new expression omega equal to A2 sine theta plus phi 2 can be represented in this way: omega equal to AI sine theta and then this symbol and then phi I. Now, I write when I is equal to 1, this symbol becomes minus, and when I is equal to 2, this symbol means plus. In this way, both the equations can be summarized in a single equation. And I have already told you the meaning of suffixes 1 and 2. So, if I recall the two cases, this is one and this is the another one. So, I can eliminate omega, the orthogonal thickness or true thickness or simply the thickness. What I am going to do now? I am going to eliminate omega. So, this expression is equal to that expression that is stated as equation number 7. This is another important relation. You can do some algebra, you can write A1 divided by A2 is equal to what, or you can expand these sine functions. Now, we want to see whether this expression is correct or not. We note in this case omega is the orthogonal thickness, and if I extend this line over here, then triangle PQR becomes a right angle triangle where angle QPR is equal to 90 degree. Why? Because omega is an orthogonal thickness, this angle is 90, therefore, this angle has also to be 90 degree. So, if this angle is theta, the dip of the plane, we can tell that angle PQR, this angle becomes 90 degree minus theta. This angle is 90 degree minus theta. So, what I can say? We can say that omega, the orthogonal thickness, is measured along a line that plunges 90 degree minus theta. What is the trend of the line omega in this case? In this particular case, the trend of the line omega is 180 degree opposite to that of the dip direction of the geological layer. Now, this information we will use further to cross check whether this deduction went correct or not. So, I recall the previous equation omega equal to A2 sin theta plus phi 2. If I put phi 2 is equal to 90 degree minus theta, from where we got, we are basically putting 90 degree minus theta. If we do so, I should get the apparent thickness same as equal to the orthogonal thickness, and indeed that happens. If you put phi 2 is equal to 90 minus theta over here, it becomes A2 sin 90 degree. Now, since sin 90 degree is equal to 1, therefore, we find omega equal to A2 as expected, which means that whatever we derived looks correct. Let us look at some of the simple numerical problems. Consider omega equal to 2.2 meter, theta is 14 degree, theta is the dip of the geological body and its orthogonal thickness is 2.2 meter. How much is the horizontal thickness h? How much is the vertical thickness v? From the formulas that were deduced earlier, use formula straightway and find out the h and the v values. I am requesting the students, even though it looks simple, you must do at least once, then you can answer in the exam. Now, for phi 1 is equal to 8 degree. What is phi 1? The symbol I already explained. Whenever the suffix is 1 in my example, it means that the drilling direction is having the same as the dip direction. Apparent thickness is measured along a line which has a trend same as the dip direction of that of the geological body, and that one is 8 degree here. Then how much is the A1, the apparent thickness for that drilling? Now, with the same data set for phi 2 equal to 70 degree, what does suffix 2 means here? Drilling has taken place to the 180 degree opposite geographic direction, and there the plunge is 17 degree. How much is the A2? So, use the formula once again and find out the value. Now, we go to the next level problem. Consider A1 is 17.2 meter and phi 1 is equal to 28 degree. This means what? There is a geological body like this and an incline drilling has been made. This distance A1 is given and this angle phi 1 is given as 28 degree, and then another drilling has taken place, but this time it is A1 dash. Since the suffix is 1 again, that means towards the dip direction of the geological unit another drilling has happened, and this time the plunge of the drilling is gentler 6 degree, and this angle phi 1 dash is given. This is A1 dash. Now, from here find out omega, theta, h and v. Omega equal to A1 sin theta minus phi 1, and we can write the another equation also, omega equal to A1 dash sin theta minus phi 1 dash. So, what are given here? The given values, A1 is given, phi 1 is given, A1 dash is given and phi 1 dash is given. And what are the unknowns? Omega is the unknown, theta is the unknown. So, we are dealing with two equations and two unknowns. So, from here one can solve omega and theta. Once omega and theta are solved, then use other equations to deduce h and v. Or we can put another problem here. Suppose this is the data set given, then for phi 1 double dash is equal to 78 degree, how much will be A1 double dash? How to do this problem? In this case, first find out omega and theta by whatever method I said, and then again use the equation omega equal to a1 double dash sine theta minus phi 1 double dash. Phi 1 double dash is known, theta is known, omega is known, and we are asking these values. Let us take another problem.